Explanation: an adjacency matrix is a two-dimensional square array A of size v times v, where v is the number of vertices in the graph. The entry aij records the relationship between vertex I row and vertex j column. Undirected, unweighted graphs. Aij equals 1 if there is an edge ij, otherwise 0. Because the edge does not have a direction, the matrix is symmetric. Aij equals a ji. Directed graphs. Aij equals 1 only if there is a directed edge I to j. Symmetry is no longer required. The matrix can be asymmetric. Weighted graphs. Instead of 1, store the weight w of ij. A missing edge is often represented by 0, infinity, or a special sentinel. For example, -1, depending on the algorithm. Self-loops. An edge that starts and ends at the same vertex I is recorded in the diagonal entry ai. In many simple graphs, self-loops are forbidden, so ai stays 0. The matrix makes it easy to ask, is there an edge from I to j? Just look at aij. It also provides a clear mental picture. Think of a city map where each row is a street and each column is a destination, and the cell tells you whether you can drive directly from one to the other and how far it costs. Explanation: to build an adjacency matrix from an edge list, follow these steps. Count vertices. Determine the maximum vertex identifier, or map arbitrary identifiers to 0 to v-1. Let v be that count. Allocate matrix. Create a v times v array initialized to 0, or a sentinel for missing edges. Iterate over the edge list. For each edge u, v, w, where w is an optional weight. Set a of u of v equals w, or 1 if unweighted. If the graph is undirected, also set a of v of u equals w. Handle self-loops. If u equals v, only the diagonal cell a of u is updated. Example edge list for a directed weighted graph. Edges equals open bracket, open parenthesis 0, 1, 5, close parenthesis, open parenthesis 0, 2, 3, close parenthesis, open parenthesis 1, 2, 2, close parenthesis, open parenthesis 2, 0, 4, close parenthesis, open parenthesis 2, 3, 1, close parenthesis, close bracket. Step 1, highest vertex identifier equals 3, implies v equals 4. Step 2, create a 4 times 4 matrix of zeros. Step 3, fill entries. Out of 0 of 1 equals 5. Out of 0 of 2 equals 3. Out of 1 of 2 equals 2. Out of 2 of 0 equals 4. Out of 2 of 3 equals 1. Resulting matrix rows. Row 00530, row 10020, row 24001, row 30000. The space used is v squared entries, that is big O of v squared. Even if the graph has only a few edges, we still reserve a cell for every possible pair, which explains why dense graphs, many edges, are a good fit for this representation. Analogy: think of a classroom seating chart where each row is a student and each column is a possible partner. Even if most pairs never work together, you still have a square table with a slot for every pair. Space analysis. A v times v matrix needs v squared memory cells. If each cell is a 4-byte integer, the total bytes equal 4 times v squared. This grows quadratically, so for 100,000 vertices the matrix would need approximately 40 gigabytes, often impractical. With an adjacency matrix, we can answer several basic graph queries in constant time. Edge existence. To check whether an edge I to j exists, simply read a of ij. If the graph is unweighted, the test is of ij not equal to 0. For weighted graphs, compare to the sentinel value. Vertex degree. Out degree directed equals the sum of row I. Deg out of I equals sigma j a of ij not equal to 0, or sigma j a of ij for weighted degree. In degree directed equals the sum of column I. Deg in of I equals sigma j a of j I not equal to 0. Degree undirected equals the sum of row I, same as column I because of symmetry. This requires big O of v time per vertex, because we must scan the whole row or column. Walk counting via matrix powers. The I, j entry of the kth power of a written a to the k equals the number of distinct walks of length k from vertex I to vertex j for unweighted graphs where edges count as 1. The proof follows from induction. Multiplying a by itself adds one more edge to each walk. Sample calculation. Consider the simple undirected graph with vertices 0, 1, 2 and edges 0 to 1, 1 to 2. Its adjacency matrix unweighted is A equals open bracket 0, comma 1, comma 0, close bracket, comma open bracket 1, comma 0, comma 1, close bracket, comma open bracket 0, comma 1, comma 0, close bracket, close bracket. Compute a squared equals a times a. A squared of 0, 0 equals 0 times 0 plus 1 times 1 plus 0 times 0 equals 1, 1 length 2 walk from 0 back to 0. 0 to 1 to 0. A squared of 0, 2 equals 0 times 0 plus 1 times 1 plus 0 times 0 equals 1, walk 0 to 1 to 2. A squared of 1, 1 equals 1 times 1 plus 0 times 0 plus 1 times 1 equals 2. Paths 1 to 0 to 1 and 1 to 2 to 1. Thus a squared tells us there is exactly one walk of length 2 from 0 to 2, and 2 walks that start and end at 1. Analogy: imagine A as a one-step travel guide. Raising it to the kth power stacks k copies of the guide, counting every possible itinerary that uses exactly k hops. Complexity matrix multiplication for dense graphs costs big O of v cubed with the naive algorithm, but for small k we can compute a to the k by repeated multiplication. Specialized algorithms, for example fast exponentiation, reduce the number of multiplications to big O of log k, but each multiplication remains big O of v cubed. An adjacency list stores for each vertex a collection of its adjacent vertices. The most common concrete form is an array or vector, Adj0 to v-1, where each entry Adj I is a linked list dynamic array or other container holding the neighbors of vertex I. Directed graph, Adj I contains all vertices j such that there is a directed edge I to j. Undirected graph, because an edge I, j appears in both directions, we store j in Adj I and I in Adj j. Weighted graph, instead of storing only the neighbor identifier, each list element is a pair neighbor and weight. For example, a struct int to double w. Self loops: if an edge I, I exists, we simply add I to Adj I once for undirected, once for directed. The list representation mirrors a phone book. Each person vertex has a list of contacts neighbors. The size of each list is exactly the degree of that vertex, so the total number of stored items equals the number of edge endpoints 2e for undirected graphs and e for directed graphs. Advantages: memory grows linearly, with the number of edges making it ideal for sparse graphs. Also, iterating over all neighbors of a vertex is big O of degree v. Explanation: to build an adjacency list from an edge list, perform these steps. 1. Initialize dash create a vector a dj of size v, each entry initially empty. 2. Process each edge dash for each edge open parenthesis u, v, w close parenthesis in the list. Append open parenthesis v, w close parenthesis to a dj open bracket u close bracket. If the graph is undirected, also append open parenthesis u, w close parenthesis to a dj open bracket v close bracket. 3. Handle self loops dash when u equals v. Add the pair once or twice for undirected if you want both directions. Example dash edge list for an undirected, unweighted graph. Edges equals open bracket open parenthesis 0, 1 close parenthesis, open parenthesis 0, 2 close parenthesis, open parenthesis 1, 2 close parenthesis, open parenthesis 2, 3 close parenthesis close bracket. Step 1 v equals 4 implies a dj equals open bracket close bracket, open bracket close bracket, open bracket close bracket, open bracket close bracket close bracket. Step 2 insert each edge. After open parenthesis 0, 1 close parenthesis adj open bracket 0 close bracket equals open bracket 1 close bracket. A dj open bracket 1 close bracket equals open bracket 0 close bracket. After open parenthesis 0, 2 close parenthesis adj open bracket 0 close bracket equals open bracket 1, 2 close bracket. A dj open bracket 2 close bracket equals open bracket 0 close bracket. After open parenthesis 1, 2 close parenthesis adj open bracket 1 close bracket equals open bracket 0, 2 close bracket. A dj open bracket 2 close bracket equals open bracket 0, 1 close bracket. After open parenthesis 2, 3 close parenthesis adj open bracket 2 close bracket equals open bracket 0, 1, 3 close bracket. A DJ open bracket 3 close bracket equals open bracket 2 close bracket. Resulting adjacency list colon 0 colon 1 arrow 2 1 colon 0 arrow 2 2 colon 0 arrow 1 arrow 3 3 colon 2. Space analysis dash the list stores exactly one entry for each directed edge, 2 entries for each undirected edge. Therefore, the total number of stored items equals big O of V plus E. The overhead of the outer array is V, and each neighbor occupies constant space, a pointer or small struct. This linear growth is far smaller than the V squared cells required by a matrix when E is much less than V squared. Analogy dash think of a city's bus map where each stop vertex has a pamphlet listing the route's neighbors that depart from that stop. Only the actual routes are printed, not every possible pair of stops. Explanation. Using an adjacency list, we can implement many common graph algorithms efficiently. Edge existence check to test if I to j exists. Scan edge I for a neighbor equal to j in the worst case. This is big O of degree of I time. Average time is much smaller for sparse graphs. Neighbor iteration, simply walk through the list. Edge I this yields all outgoing edges of I in big O of degree of I time. Degree computation, the degree of vertex I is edge I size, out degree for directed, total degree for undirected. This is big O of 1 if the container stores its size, otherwise big O of degree of I to count. Breadth first search BFS. BFS explores vertices level by level. Pseudocode with adjacency list. QQ visited V equals false. Q dot push S visited S equals true, while not Q empty U equals Q pop. For each VW and edge UW is ignored for unweighted BFS. If not visited V, then visited V equals true, Q dot push V. Depth first search DFS similar but using a stack or recursion. Function DFS U colon visited U equals true. For each VW and edge U, if not visited V, then DFS V. Real-world analogy, imagine you have a phone directory where each person's entry lists all the people they can call. To find out whether Alice can call Bob, you look through Alice's list. To spread a rumor, BFS, you call all of Alice's contacts, then all of theirs, and so on, each call happening at most once. Complexities, edge existence. Big O of degree of I versus big O of 1 for matrix. Neighbor iteration. Big O of degree of I optimal versus big O of V for matrix must scan whole row. Adding removing edges. Big O of 1 amortized for list push pop versus big O of 1 for matrix just set a cell. However, removing from a list may require scanning the list to find the entry costing big O of degree of I. Explanation colon the choice between adjacency matrix and adjacency list hinges on the trade-off between space and operation cost. Add edge, O of U sub V equals W leads to O of 1 time, O of 1 extra space. Append to edge of U and edge of V if undirected leads to O of 1 amortized time, O of 1 extra space per edge. Remove edge, O of U sub V equals 0 or sentinel leads to O of 1 time. Find and delete entry in edge of U and maybe edge of V leads to O of degree of U in the worst case, average much smaller. Adjacency query, edge existence. Direct lookup A of U sub V leads to O of 1. Scan edge of U leads to O of degree of U, worst case O of V for dense graphs. Iterate all neighbors of a vertex. Scan entire row of length V leads to O of V walk through list leads to O of degree of U, optimal. Space stores V squared entries leads to O of V squared. Stores V plus E entries leads to O of V plus E. Best for dense graphs, edges approximately V squared, fast edge tests, matrix algebra powers, eigenvalues. Sparse graphs, edges much less than V squared, algorithms that need neighbor traversal, breadth first search, depth first search, Dijkstra. Key intuition, the matrix is like a full grid of possible roads. Every intersection to every other intersection has a cell, even if most roads do not exist. The list is like a map that only draws the actual roads. You never waste space on non-existent connections. When to switch, if the graph becomes dense, for example greater than 0.1 times V squared edges, the list's extra overhead, pointers, dynamic allocation may outweigh the matrix's waste, and operations that need constant time edge checks become more attractive. Summary of asymptotics, adding or removing edges both O of 1 list may need O of degree to find the edge for removal. Edge existence, matrix O of 1 list O of degree. Neighbor iteration, matrix O of V list O of degree. Space, matrix O of V squared list O of V plus E. Explanation, Matrix powers give a beautiful way to count walks. For an unweighted graph with adjacency matrix A, the entry A to the k, ij equals the number of distinct walks of exactly length k from vertex I to vertex j. This follows because matrix multiplication adds one more step to each existing walk. Illustration with a 4-vertex graph. Vertices are 0, 1, 2, 3. Edges are undirected 0 to 1, 0 to 2, 1 to 2, 2 to 3. Adjacency matrix A unordered 1 for an edge is as follows: row 0, 0, 1, 1, 0, row 1, 1, 0, 1, 0, row 2, 1, 1, 0, 1, row 3, 0, 0, 1, 0. Walks of length 2. Compute a squared equals a times a. The entry a squared sub 0 sub 0 equals 0 times 0 plus 1 times 1 plus 1 times 1 plus 0 times 0 equals 2, representing the walks 0 to 1 to 0 and 0 to 2 to 0. The entry a squared sub 0 sub 1 equals 0 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0 equals 1, representing the walk 0 to 2 to 1. The entry a squared sub 0 sub 2 equals 0 times 1 plus 1 times 1 plus 1 times 0 plus 0 times 1 equals 1, representing the walk 0 to 1 to 2. The entry a squared sub 0 sub 3 equals 0 times 0 plus 1 times 0 plus 1 times 1 plus 0 times 0 equals 1, representing the walk 0 to 2 to 3. Fill other rows similarly. The fullest squared matrix is: first row 2, 1, 1, 1, second row 1, 2, 2, 1, third row 1, 2, 3, 0, fourth row 1, 1, 0, 1. Interpretation: there are two walks of length 2 that start and end at vertex 0. There is exactly one walk of length 2 from 0 to 3, namely 0 to 2 to 3. From vertex 2 to itself, there are three walks of length 2, 2 to 0 to 2, 2 to 1 to 2, and 2 to 3 to 2. Length 3 walks, compute a cubed equals a squared times a, or use fast exponentiation. The numbers grow quickly, representing all possible roots of that length. Why it matters? In network reliability, the number of length k walks can model the number of ways a message can travel in exactly k hops. In chemistry, a to the k counts possible reaction pathways of length k. Mathematical note: for weighted graphs, if aij stores the weight, then a to the k ij gives the sum over all walks of the product of edge weights, useful in Markov chain analysis. Computation tip: for large sparse graphs, using the adjacency list and repeated multiplication with sparse matrix techniques is far more efficient than dense matrix multiplication. Open parenthesis, a close parenthesis, write both representations for a given graph. Prompt: given vertices a comma b comma c comma d and edges a comma b, a comma c, b comma d undirected unweighted, write the adjacency matrix and adjacency list. Answer pattern: 1. List vertices in a fixed order, e.g. a equals 0, b equals 1, c equals 2, d equals 3. 2. Fill a 4x4 matrix with 1 where an edge exists, diagonal stays 0. 3. Show the matrix rows. 4. For the list, create 4 lines: a colon bc, b colon ad, c colon a, d colon b. 5. Mention that for undirected graphs each edge appears twice. Open parenthesis b close parenthesis, convert matrix to list. Prompt: convert the following adjacency matrix to an adjacency list. Answer pattern: scan each row I. For every column j where entry is not 0, append vertex j to edge sub I. Write the resulting lists. For the reverse direction, read each list and place a 1 in the corresponding matrix cells. Open parenthesis c close parenthesis, analyze complexity of a specified operation. Prompt: what is the time complexity of checking whether vertex 5 has an edge to vertex 9 in an adjacency list representation? Answer pattern: state that we must scan the list of vertex 5. Complexity equals big O of degree 5 in the worst case, less than or equal to big O of v. Contrast with matrix O1. Open parenthesis d close parenthesis, compute number of length 2 paths using matrix multiplication. Prompt: given the adjacency matrix, find how many walks of length 2 go from vertex 0 to vertex 2. Answer pattern: 1. Multiply the matrix by itself, show the formula for entry 0, 2. 2. Compute a squared sub 0, 2 equals the sum from k equals 0 to 2 of a sub 0, k times a sub k, 2 equals a 0, 0 times a 0, 2 plus a 0, 1 times a 1, 2 plus a 0, 2 times a 2, 2 equals 0 times 0 plus 1 times 1 plus 0 times 0 equals 1. 3. Conclude that exactly one length 2 walk exists 0-1-2. General advice for exam answers. Always state assumptions directed or undirected weighted or not vertices indexed, starting at 0 or 1. Use tables or bullet points for clarity. When asked for complexity, write both the big O expression and a short justification. For matrix-based counting, write the summation formula before plugging numbers. This shows the reasoning. Keep the answer concise, but complete exam graders reward a clear step-by-step layout.